Hello, I'll be using this video to go through with you your class test that is done in term 4. Now, after you watch this video, it is very important for you to actually do your own correction. You can do it directly on the paper in a different color pen. It can be red, it can be green, it can be in pencil as well. But make sure that there's enough space for me to properly read your correction so that I can tell that you have understood the concept. You have understand the concept. Okay, let's begin. So for question 1, it is a question on sound. Now, the question basically is trying to tell you that there is this fellow, the trainer. He is actually tapping on the water to make sound. And basically the sound will travel to the dolphin. Now, I have a number of you who thinks that the sound is made in air. So you are thinking that, oh, okay, the sound actually goes into the air, and then after that, somehow it will refract into the water. Now, this is a very wrong concept because when you vibrate the water here will also get vibrated. And as a result, the sound can travel directly from the trainer's hand to the dolphin. So actually, you do not need to go and talk about how sound travel in air and then after that it refracts into the water. You don't need to do that. So the first question here in part A, you are asked to actually describe how sound travel through the water to reach the dolphin. So this is a question that we have done during the revision, and I have been trying to hint to you that you need to memorize this. In fact, it is a popular question in O-level. So down here, you can see that in my answer on screen, there are actually 4 parts, which is labeled 1, 2, 3, 4. Now, when I mark your paper, if I find that you have missing some part of the answer, I will write down something like, so let's say this is your answer, you write, and then I will go and put like a tick, and then after that maybe a tick and a cross, and I will put like ... 4. So this means that point number 4 is missing from your answer. So that's how you should be reading my comments on you on your answer. So let's go back here. Now, how to answer this question, right, or in fact how to memorize this is number 1, you need to identify where is the source of vibration. And it is very important that you refer to the molecules, the molecular level. You shouldn't say the water vibrate, but rather the water molecule vibrate. And you need to tell me what is the trigger for this vibration. What is the cause of this vibration? After that, it is very important for you to actually highlight in your answer that this vibration is first transmitted to the water molecule that is next to the source of vibration. So this keyword neighboring become crucial in your answer, and we only accept this one adjective. So you must memorize it. Okay? Then after that, it is the standard. After you transmit the vibration to the neighboring particle, you are not just making your neighbor vibrate, you are creating a series. So therefore, this particular phrasing, right, is required. So you must tell me that it creates a series of compression and refraction, not just one pair, but a series. And finally, you need to be able to rephrase and tell the examiner that you are aware that the sound is a longitudinal wave. So to get these 2 marks, you need all 4 parts of the answer. That's why you see that there are 4 answer lines. So you should base on the number of answer lines to gauge how much detail you would want to commit. Okay, for part B, most of you are able to see that you should use V equals to F lambda, but only a very small number of you are aware that the unit given here is in kilohertz. So if you look here closely, you will see kilo. And I have been telling you all that as a good habit, whenever you are doing physics question, you should always circle whenever you see something like this standing out, the kilo. And the correct way of converting it is 40 kilohertz. How do you get 40,000? you change the k into 10 to the power of 3. So if you use your calculator, you will find that your 10 to the power of 3 is basically 3 zeros. Okay, and if you do your mathematics correctly, you should be able to get your wavelength and you should round it up to 2SF. So that's your part B. Okay, for part C, it is quite disappointing. Yeah, because I can see from your answer that many of you are not aware that the medium, meaning that whether it is traveling, medium means whether is it in air, or is it in water, or even is it in a solid. So the type of medium will actually determine how fast your sound will travel. So in general, if you have a high density medium, you would be able to have a speed that is high. Okay, they are correlated because if you have particles that is very dense, meaning that your particles are very near to one another, when one particle vibrate, it will be able to transmit this vibration to the neighbor very, very quickly. So we say that if your medium is of high density, the speed of sound will be high. Okay. Some of you are using refraction to a refractive index to answer. So for your refractive index, okay, your refractive index refer to this n equals to c over v, right? This refractive index is for light only. This guy is for light only. So in physics, especially in O-level physics, whenever you are asked to actually explain something, it is always best that you quote the formula that is useful. Okay, so let's recap on this question first. So here it says that the dolphin jumped from water to air, and the frequency of sound emitted by the dolphin does not change. Explain why the sound wave in the air, okay, have a shorter wavelength than they do in water. So what happened is that the question is asking you, can you please explain to me why the wavelength in air is smaller than the wavelength in water? So because air is in gaseous state and water is in liquid state, you will be able to tell that for your air, the density is actually lower, right? So you can see that this part here, in water, the liquid, right? Here the density is high. So we have already learned just now that when the density is high, you can see here, when the density is high, the speed will be high. So down here, you will be able to tell if you have this piece of information that the speed is high, right? So therefore, you can actually look at the formula V equals to F lambda. If now your speed is high, right, and the frequency is constant because you are making the same sound, then what it means? It means that your this thing over here, okay, will have to be larger in water, right? Because down here your speed is high in water, correct or not? So when the speed in water is higher, then definitely your lambda will be higher in water. So far so good. So to put this concept in words, there are two parts. Number one, you must be able to tell me that the speed of sound in water is faster than in air. And then you must be able to quote the relevant formula. And after that, you need to tell me that, oh, since the speed in water is high and that the frequency is constant, therefore your wavelength in water must be longer. Okay, so here I think I make a typo. So your wavelength in water will be longer. In another word, your wavelength in air will be shorter, right, than your wavelength in water. And this is what you want to prove to the question, right? So that is your question part C. If you do not understand this, you need help, do text me. You can just WhatsApp me and say that, teacher, I still don't get it. Okay, because it is very, very important that you clear all your doubt before you step into the examination hall. Yeah? Okay, next we have question 2, which many of you have done a fabulous job. So in the first question, they are asking you to find refractive index. So there are two ways to find refractive index. Number one is, if you know the different speed, you can use formula 1. But in this case, there is no information on the speed of light inside the glass, inside material X. So we are unable to do this. Okay, so now we have to use approach number 2. Approach number 2 is your Schnell's law. So you can apply your Schnell's law, n sine theta equals to n sine theta. You can pick, maybe this side is air, this side is your material X. So you can see that in the air side, this is your air side, the angle between the normal and the ray is 43. So then you can now substitute 43 inside here, and n of air is always 1. Then after that, you want to find the refractive index of material X, so you write there, and this is your material X side. The angle between the normal and the ray is 33. So now if you go and solve this equation, you will be able to find the refractive index of X, and you should turn it into 2SF. Okay, this one I leave it to you to figure out. Okay, for critical angle, you can use two approach as well. There is a formula that allows you to find critical angle directly, which is sine C, that is your critical angle, equals to 1 over n. Okay, but in this case, there's a limit. Okay, this equation only work for air and medium. Meaning to say, what does it mean by air? One of the medium has to be air. Okay, if it is a case whereby it is material X and then material Y, you will find that this equation will not work. Okay, so what I advise students do is to just memorize one thing. You can also find the critical angle using Schnell's law. It is very similar. N sine theta equals to n sine theta. One side is air, the other side is your material X. So how do I find critical angle? Okay, to find your critical angle, there are some conditions that you need to memorize. Number one is the theta in the lower n medium must be 90 degree. Okay, so what does this mean? For example, if now I have medium X, this is my material X, I want to find a critical angle. What does critical angle means? It means that there will be a beam of light shining to the boundary, and when it shines to the boundary and when it wants to exit the boundary, it will exit it this way at 90 degree. So when this happens, this particular incident angle, we give it a special name. It is called critical angle. So because of this particular property, if I want to find this particular angle, what I need to do is quite straightforward, right? In the air side, my angle will be 90. So I will substitute here 90 sine and refractive index of air is 1. Must be equals to, I have already found the refractive index of X. Correct or not? So down here, I would have already found, this is my part A answer. Right? This one I find from part A. And then I would have sine. Now here, the angle in material X would refer to this angle, right? Which is now called the critical angle because my corresponding refracted angle is now 90. So on this side of the equation, I can then put down C. So if you go and solve this equation, you will be able to get the answer. And for angles, same thing, 2SF. So for all your theory paper, right, everything is in 2SF. Okay, go and work out, and then I will mark your correction. Okay, for your part C, this is actually a build up extension from here. You should know that when the light ray strike the boundary at critical angle, the light ray will actually behave like this. Okay, go along the boundary. I have some of you who think that when it reaches the edge here, it will somehow refract. No, it doesn't. There is no change in optical density, right? It will just keep on going straight to infinity and beyond. Okay, so you need to actually label that this dotted line is normal. You need to spell it out because they ask you to label clearly. You also need to tell me that this angle is actually your critical angle. And of course, your angle of refraction, you have to use a 90-degree symbol because it is 90 degree. And then you let me know that this is your angle of refraction R. I only realized it that you can use short form. So you don't even need to spell it out. You can just call this N, and then you can just call this small c. So far, okay? Okay, now for part D, they are checking whether you know how to make use of the critical angle. So they are telling you that this particular incident angle, which is here, right, this angle I is actually larger than the critical angle. So larger than critical angle. So with this criteria, right, you will actually need to know this. What does this mean? This means that your critical angle is a constant, right? This guy is a constant. It depends on the material, right? But the angle of incident can change, right? You can shine the light in at different angles. So let's say I have a block of glass, right? I want to shine the light here. I can shine the light like that. I can shine the light like this. I can shine the light like this. By shining the light at different angle, my angle of incident will be different, right? Can see? Blue, red, and black. So this blue color angle of incident is an independent variable. This one depends on the user, right? The user can decide what is the angle I. So what happens is that by choosing different number, let's say my critical angle, let's say it is 40 degree. Okay, so for material X, critical angle will be a fixed number. And you can decide, oh, okay, I may want to shine the light at exactly 40. I can also shine the light at maybe 20 degrees C. I can also shine the light at maybe 80 degrees C. So depending on the critical angle and depending on your angle of incident, you will have very different outcome. Now, when the incident angle and the critical angle are the same, you will see that the refracted light will go at the boundary, right? It will go along the boundary and to infinity and beyond. Now, if you are looking at this case whereby the incident angle is much smaller than the critical angle, then what happens is that the light will be able to get out and it will get refracted away. And of course, the last possibility is if now your angle of incident is way larger than the critical angle, then what happens is that the light ray will get trapped. This particular phenomenon is called total internal reflection. So if you know this piece of content, then this question will be quite easy because they already tell you that you are shining your light, incident angle is larger than the critical angle. You can see it over here on top. Okay, here, the pink one. So once you know that, then you just need to make sure you draw with an arrow, and you need to be able to tell me that this angle and this angle must be the same. Now my eyes, because I can draw pretty well, I'm quite sharp to detect whether your angle are the same or not. So I allow up to a deviation of 1 to 2 degree. Yeah? Okay, question 3. Question 3, we have been trying to hint to you that we don't teach you everything. So this is your set 2 content. So basically when you are looking into water, because of the change in refractive index, you will see that there will be a virtual image and the coin and basically the depth will always appear to be more shallow. So how you do? So this is your step number 1. Step number 1 is quite straightforward. You just need to trace this solid line, and then you extend it out into the air. This is your perceived ray. That means your brain will think that it is just going straight. But knowing refraction, when you move from water to air, how will the light bend? Does it bend away from the normal, or does it bend towards the normal, which is this dotted line over here? So you think about it before you carry on. So I hope you remember that when light travels from high density to low density medium, it will bend away. So this is how it will bend away. It's just agak-agak. Okay, you won't be able to measure it. Okay, so same thing, it will bend towards away from the normal. Down here it will bend even more. So maybe like that. So how do I know that this yellow one should bend more than the green one? I look at the incident angle. So if this is I1 and this is I2, you will be able to tell that actually I1 is larger than I2, and hence your R1 must also be must be smaller. Oh, sorry. Your I1 is less than I2. So your R1 is also less than your R2, which is here. Okay? So once you have done that, you still have not drawn your apparent position of the coin, right? So what you do, you look at the green highlighted line. From the green highlighted line, use your ruler, this green highlighted line, you make it straight. Then you look at the yellow color line, which is this guy over here. Same thing, extend it. So extend. Can you see that it will converge here? It means that the coin will appear here. Okay, like I said, all these are estimate. So as long as you show me that your R1 is less than R2, this is your R1, this is your R2, and you show me that after drawing the refracted ray, you are aware that you need to extend it, and you extend the yellow one also until you find this intersection. this is the apparent position for your coin. Okay, so if you are having trouble understanding this, like I said, please WhatsApp me and then I can help you. So to recap, step number 1, okay, draw the perceived ray. Step number 2, draw the refracted ray, okay, from here to here, from here to here. Then step number 3, you extend the refracted ray into the water. Okay? Okay.